Franz, Gregor Leander, Louis Doppelen, and Friedrich Weimer.
Okay, thank you. So, welcome to my talk about short and linear straight line programs for MDS matrices, aka yet another exocount paper. Okay, so I start with a short motivation. We are also in this scenario of lightweight cryptography, so we have a cryptographic system in some constrained environment, and we also, like the previous talk, have the typical goal of minimizing the chip area of the implementation. And we're going to focus on linear layers here, which is one of the main building blocks of most symmetric primitives. So linear layers consists of matrix multiplications, and often these are MDS matrices, because MDS matrices have very good optimal diffusion properties. And here's an example of the AES mixed color matrix, probably everybody knows. Okay, so now if we want to find a small implementation in terms of area for such a matrix multiplication, we are having this scenario here. So we also focus on round-based implementation. That is, we have our input bits. In the case of this example, it would be 32 input bits because it's 4 bytes. And we need to compute 32 output bits. And in here there will be some Boolean logic gates, but no memory or no clock whatsoever. And we try to keep this as small as possible. Okay. So this is a very typical metric we use here. It has been presented before, the XOR count. So we restrict to XOR gates. Basically this means, okay, here we have the same scenario, but we only use XOR gates within here. And these are 2-bit XOR gates in our case, basically always. So the idea, of course, is that if you have the low XOR count, then you would also need a low chip area, which is, of course, a simplification, as we have also learned. And just note here that if you have this scenario, any intermediate result might be reduced. So if you at some point here compute some output by some XOR gate, you can always use it at some later point as an input, because it's just wiring within a circuit. So in our scenario, any result that has been intermediately computed at some point can be reused later in the circuit. Okay, I'm first going to present some of the previous work and the way people have been mostly counting the XOR of matrix multiplication so far. Then I'm going to talk about a bit separate line of research called short and linear straight line programs, and we'll see that this actually helps us to improve the previous work in terms of number of XORs for matrix multiplications. Okay, this is just an excerpt here. Actually, there's many more papers recently been presented and published, and dealing at least partly with XOR count and optimizing the XOR count of matrix multiplication. So we see a lot of FSE stuff going on here. And what have they done? So mostly they have been searching many matrices. So they have taken typical matrices that are either by construction MDS or that tend to be that are MDS with higher likelihood. So, for example, Cauchy, Vandermonde, and so on. All this has been done in this work, or also arbitrary matrices, meaning no specific structure. And basically searching as many matrices as possible and trying to find the one with the lowest XOR count. Okay, and then of course, people have tried to optimize the element multiplication. So if you have a matrix defined over some finite field, you try to find the elements that where the element multiplication can be implemented with very few XORs, and then use these constructions and the according elements to build efficient MDS matrices. Okay. Let's talk about how people have been counting XORs needed for matrix multiplication. Okay, so we have this matrix here, and we want to compute this multiplication. So people so far have typically split the XOR count in overhead and fixed cost. So overhead would be the number of XORs needed for carrying out the single multiplications. Okay, so if we want to compute y1, we would need to multiply alpha 11 times x1 and alpha 12 times x2 and so on, and until alpha 1n times xn. We would do this for every row to multiply to compute all the outputs until the last row. So we really have to implement, if we think of it like this, we have to implement multiplication with every element of the matrix. And so this is what's called the overhead. And here, this is then the sum of the XORs needed for every element multiplication. And then, of course, if we have computed these products, they need to be added up. This is called the fixed cost. So this is just the cost of adding up these additions. So we have computed alpha 1 times x1, and then plus alpha 2 times x2, plus, and so on. So these additions. And how many additions are this? We have n rows. This is where the n comes from. In each row we have computed n products, so we have n minus 1 additions. And if these elements are from the field f2 to the k, this makes k bit XORs. So this is where the fixed cost, n times n minus 1 times k comes from. And if you see it like this part is completely inevitable. So it's unavoidable. It's a lower bound. And so people have only focused on this part, on optimizing these single element multiplications, and actually even not consider the fixed cost at all. So typically, many publications would just publish the overhead. So let's just have a short look at previous best results, so far as I know. And this is now split up into the left part, which is always the overhead, and the right part, which would be the fixed cost. The upper half here is just MDS matrices, and the lower half are involutory MDS matrices, and we have different dimensions as both sides. And if you compute the sums, this is what you see. The actual really overall number of XORs needed to implement these matrices. And we'll come back to these results later for comparison. Okay, now something apparently different, but in reality it's not different. What have we done so far when thinking about matrix multiplication? We have optimized these single element multiplications. So maybe I should mention this because not everybody might be aware of this. We think of these single matrix multiplications where the field is f2 to the k as k times k binary matrices, because it's a linear operation, f2 to the k, so it's f2 linear. Can be represented as a k times k binary matrix, and then we would try to optimize the number of XORs needed. But if everything here can be represented as a k times k binary matrix, you can also just represent the whole thing as an n k times nk binary matrix. And why wouldn't we optimize this? Because obviously now we have much more degrees of freedom for optimization. Well, I guess it's probably two reasons. The first reason is that people have been thinking of matrix multiplication in this abstract way, as I just presented, by multiplying the single elements and then adding them up. And the second reason is probably that the algorithms that have been used for these single optimizations here cannot be used for a large dimension. So it's too complex. And this is actually not surprising because this problem is known to be NP-hard, the problem of finding the implementation of a binary matrix multiplication with as few XORs as possible. So why do we know this? Because there's a separate line of research dealing exactly with this problem. And what they call it shortest linear straight line programs. And you see it's kind of different kind of conferences, so maybe this is the reason why people have overlooked it so far, although there's something here in the Journal of Cryptology. Well, apparently has been kind of overlooked so far. Okay, so what do they do? What's a short linear straight line program? What's a linear straight line program? A linear straight line program is just a program using only, in every line it would use one addition. And at the beginning you only have the inputs, and then at a later point you can use everything that was computed at some point. So this means it's exactly what we need. It's exactly what I motivated in the beginning, because you just use additions, so you try to get a few XORs, and you can reuse anything computed at some point. And as I said, it's NP-hard, so you cannot expect to find an algorithm to find the best solution, but they are heuristics. And we're going to shortly look at one, which is already very old. It's 20 years old, and it's very easy. And as we will see, it's already quite effective. Okay. So this is a toy-size example, but this, of course, also works for larger dimensions. For example, if you want to optimize A as mixed column, this then would be a 32 times 32 binary matrix. So this algorithm from PAR is just always searching for the next most common sub-expression and computing this. So what does this mean? Here we would look at the matrix, and here look at what's the most common sub-expression. In this case it's, for example, A0 plus A2. So this is the first thing we compute, and this is the first line of our straight line program. And now we replace this by X0. All right, and now we just do the same again. Oops. Sorry. Okay, so we now again look for the next most common sub-expression, which would be this one. Compute this as the next line of our straight line program, and replace it by the new variable. And so on and so on. This is everything. And now actually we are at a point where there is no common sub-expression anymore, so we'll just compute these 1, 2, 3, 4 additions straightforward, and this yields a implementation or straight line program with 6 XORs, although we would have done it in a naive way. It's 9 XORs. So it seems really almost trivial, but actually it works fine. And we have run this on the previous results. So these are the same matrices, not new matrices. These are the same matrices, and we just improved the implementation. And as you can see, already sometimes quite significant improvement from this very simple algorithm. So at this point, you're really noticing that there seems to be something overlooked here. And actually, this is not the end, because this algorithm is from 1997 and this work has gone on, so there has been follow-up work and more efficient, more sophisticated algorithms than this pretty straightforward. So just to give you an example, taking the same matrix, you could also just compute A0 plus A1 plus A2 plus A3. And now you would already have 2 of the outputs. And now you can also make use of cancellations. So you take now this intermediate value and add A1 or A0, and the according variable cancels out, and you have everything now at 5 XORs, which is even more efficient. So there are more sophisticated ways of doing this. Yeah, and the results are correct. So, what did we do? We applied these existing heuristics to the matrices from the previous work that have presented. Excuse me. And also, basically, to any MDS matrix or even not MDS matrix, you can find in the literature from any block cipher or hash function. The complete results are in the paper. But the basic message is that we could everywhere find improved implementations, so a lower EXA count, and maybe the most interesting results is the AES mixed quantum matrix, that we could also come up with a more efficient implementation in terms of EXA count. Okay, and afterwards we also did some statistical analysis. That is, we took these constructions that are typically used to find MDS matrices, and we wanted to find out if there's one that seems to be superior in terms of EXA count. And the result is that we couldn't say that one was superior, but there's one exception, namely if you use a subfield construction. The subfield construction is a way of transforming a smaller matrix into a bigger one, so you have some matrix basically for 4-bit S boxes, you can transform it into a matrix for 8-bit S boxes. And this really yielded better results than if you would just randomly use these constructions. So it might be a good strategy if you're not able to exhaustively search the space to use the subfield constructions if you have results for smaller S boxes. Although this, of course, doesn't mean that the best matrices will be matrices that can be represented as the subfield construction. But it seems to be a good strategy, and this claim is supported by the fact that whenever the subfield construction can be used, whenever the subfield construction can be used, it was the subfield construction that yielded the best results in our experiments. So my voice is kind of dying, so I'm just going to quickly show you the results. This is now nearly everything and new matrices, so we come up with complete new matrices here, except I think this case, this case here, there we didn't find a matrix that is more efficient than some matrix already existing, but we could improve the implementation. Okay. And if you now artificially present it in the previous notion, that is overhead and EXA count, actually we would have a negative overhead. And the reason is, of course, that we don't implement the matrix multiplication not by doing the single element multiplication and then adding them up, but we use a global optimization on the huge binary matrix. And so you could never reach these results if you think of it in the traditional way, because then this right half here would be a lower bound. And this leads me to the conclusion. As I think is clear from the previous slide, you should do the global optimization because you can achieve better results than possible if you just think it over at fixed cost and do the local multiplication. And there are heuristics out there from this kind of separate line of research, so they should be used. And of course, it's not necessary to restrict to matrices over finite fields. But you can basically take elements from the general linear group. Our results are online, including all the straight line programs. Yeah, sorry for my voice.
So we have time for a very, very short question.
Thanks. So my question is pretty naive. I noticed in the example you gave where you picked the most common expression here. I think even in the example you gave, there were actually several sub-expressions that had the same number of occurrence. So it means that you can pick one. So when you run these heuristic algorithms, do you typically randomize on this and run it several times and look at the best result you get in the end?
So Christoph Paar in his work presented two algorithms. The first one was just always picking the first occurrence. So you would, basically you're comparing columns of the matrix, and you would just choose the first one which leads had the best most common sub-expression, and with this algorithm is super fast. And then he presented a second one where you recursively do it and try everything, and this is quite slow, but we also use this algorithm, and we let it run, let's say, sometimes 3, 4, 5 hours, and then shut it down, and it also sometimes yielded better results. But yeah, of course, you could also randomize, I guess.
Okay, but the first one that's really fast, you didn't try to do it several runs and...
No.
Okay, thanks.
Anything else?
I don't want to torture your voice much more, but can you maybe very briefly comment about the length of the critical paths of your implementations as opposed to the previous ones?
We didn't look at the depth, so I have no results to this, I cannot say. But these existing heuristics from this presented at so the second publications I presented, they now recently, I think a few months ago, also published a paper which optimizes for circuit depth. So there's also work out there that can be applied to this problem, but we didn't.
All right, thank you.
So it's time to move to the next talk. We are teeny tiny bit late. So let's thank Thorsten again. And we're moving on to the next talk.